Welcome to the amazing Mandelbrot set tutorial. If you're interested in a thorough understanding of the Mandelbrot set, you've come to the right place. We're going to tell you everything you need to know to fully appreciate the deep zooms on this disc. But to keep this lesson as brief as possible, we'll only tackle a couple of issues. They are, what does the Mandelbrot set represent? And how is it generated? These are very basic concepts, so don't worry, the math will be simple. In the purest sense, the Mandelbrot set is simply a group of numbers that display a certain unusual property. But since the set is always associated with an image that represents this property, we'll often use the term Mandelbrot set to describe the image itself. With that in mind, let's start with a general description. The Mandelbrot set is a visual representation of an iterated function on the complex plane. Obviously, this doesn't make a lot of sense if you haven't studied iterated functions or the complex plane, so you'll need to know what both of these things are. Luckily, they're easy to explain. Let's start with iterated functions. As you already know, a function is just a series of one or more mathematical operations that can be performed on any number. A function has an input, which is a number you supply, and an output, which is the result of performing those operations on your input number. Functions are written in this form, f of x equals, and this is followed by the mathematical operations performed on x. Look at the function f of x equals x plus 1. All this function does is to add 1 to any number. To use this function with 2 as your input, you let x equal 2. You'd say f of 2 equals 2 plus 1, or f of 2 equals 3. An iterated function works just like a regular function, except that it's performed over and over again, with each output used as the next input. You can iterate any function just by repeating it in a loop. This is what our example looks like as an iterated function with the number 2 as our first input. As you can see, the outputs keep increasing by 1. It's actually a pretty boring function because the sequence of outputs is totally predictable. Now consider another function, f of x equals x squared plus c. In this example, c can represent any number we want it to be. But when we iterate this function, whatever number we choose for c will also be the function's first input. We'll refer to c as our first input because it's going to be the same number anyway. This function will take any number, square it, add back the original number, square that, add back the original number, etc. When 2 is our first input, look what happens to the output sequence. The numbers get really big, really fast. This tendency to zoom off toward infinity is an example of exponential growth, and it's the general rule for this function. The same type of behavior will occur with every input number greater than 1, and even every negative number less than -2. However, between -2 and +1, weird stuff happens. We're going to explain this in some detail because this behavior is the basis for the Mandelbrot set. First, let's see what happens when we use a very small positive number as our input. As you know, squaring a number just means multiplying it by itself. Anytime you square a number less than 1, the result is an even smaller number. When you square 1/10, your answer is a tenth of a tenth, or 1/100th. If you add back a tenth, you'll get 0.11, an answer that is only slightly larger than your original number. Iterating 1/10, you'll notice that even though the outputs do increase, they increase by smaller and smaller amounts. At this rate, you can iterate the function forever without ever reaching 1. Instead, the outputs will converge on some value close to the original input number. This convergence behavior is one exception to the general rule of exponential growth for this function, but it's not the only one. Numbers between -2 and 0 behave differently due to the interaction of two simple rules of arithmetic. First, whenever two negative numbers are multiplied together, their product is always positive, which means that the squares of all negative numbers are positive. And second, adding a negative number is the same as subtracting its positive value. These two rules work against each other in the iterated function x squared plus c. If you input any number between -2 and 0, The positive gain you get by squaring it is diminished by adding back the original negative number. If we iterate -1 in this function, the outputs alternate between 0 and -1 forever. Now look at the iteration of -2. -2 is a special case because 2 is the only number that gives the same answer whether you multiply it by itself or add it to itself. Because of this special property, using -2 as your first input in this function will result in an endless sequence of 2's. Other values between -2 and 0 behave even more strangely in this function. They may bounce back and forth on a small segment of the number line, never straying too far from 0 and never hitting the exact same value twice. The outputs don't get exponentially larger, and they don't converge towards a single value. Instead, they wander. It's hard to call this behavior unpredictable, since it's completely determined by a single mathematical rule. And because of this, it does exhibit some hidden pattern. Still, it's remarkably difficult to guess what the output sequence will look like. This type of behavior is called chaotic behavior. Stranger still is what occurs when we iterate the same function with a very special class of numbers called complex numbers. Complex numbers can seem unusual at first because they don't occur anywhere on the number line. To describe them, we'll have to go back to the basics. We already mentioned that the squares of all negative numbers are positive. This means that both -2 and +2 have the same square, +4. It also means that the square root of 4 has two possible solutions, +2 and -2. So what would you make of this number, the square root of -4? You might think it can't exist, because no real number can be squared to equal a negative number. But since numbers like this occur in valid equations, they can't be ignored. And when we treat them just like real numbers, we find that they obey the same rules. So even though we call them imaginary numbers, they exist as much as any other numbers. A complex number is the result of adding a real number to an imaginary number. Since the sum of these two numbers is neither completely real nor completely imaginary, we call it a complex number, and we leave the two parts separate, even though they're considered a single number. To get this complex number into its standard form of expression, we have to do one more thing: factor out the square root of -1. Since -4 is the same as +4 times -1, the square root of -4 is the same as the square root of +4 times the square root of -1. So we can separate them into two factors. Then the square root of 4 is simplified to 2. Now we have our complex number in the standard format: a real number plus another real number which is multiplied by the square root of -1. We call the square root of -1 I for imaginary. This number is so special in mathematics, it has its very own name. Complex numbers are written in the form a plus bi, which is important because it allows them to be used easily in calculations. It also allows them to be ordered in a grid called the complex plane. The complex plane is just an extension of the number line into two dimensions. The horizontal axis of the plane is the real number line, and the vertical axis is the imaginary number line. Every complex number has its own unique address on the complex plane, defined by the value of its real and imaginary components a and b. To find the exact position of any complex number on the plane, all you have to do is locate the intersection of the real component and the imaginary one. For the complex number 3 plus 2i, move over 3 units to the right and up 2 units. Hard to believe, but the complex plane is that simple. At this point, it should make a lot more sense to hear this description a second time. The Mandelbrot set is the visual representation of an iterated function on the complex plane. In fact, it's the same function we've just studied. And now that you understand the strange results of iterating this function with real numbers between -2 and +1, it's time to look at what happens when we use complex numbers in the same neighborhood. Let's look at the complex plane again. Just as any real number less than -2 or greater than +1 will grow exponentially in the function, So will any complex number outside a circle of radius 2 centered on the complex plane. The Mandelbrot set is technically defined as the set of all numbers that do not grow exponentially in the iterated function x squared plus c, and they're typically represented by the color black. This is a computer-generated image of the complex plane, showing all the possible numbers within the Mandelbrot set displayed in black. Now, let's iterate the function for the number 1 plus 1i and see what happens. As we said, complex numbers obey the same rules as other numbers. They can be added, subtracted, multiplied, and divided, just like any expression with two terms. If we square 1 plus 1i, we find that it's equal to 2i. Watch. 1 times 1 equals 1, and 1 times 1i equals 1i, and 1i times 1 equals 1i, and 1i times 1i equals negative 1. Remember, I represents the square root of negative 1, so its square is negative 1. Add up the terms, and the sum is 2i. We still have to add back the original number 1 plus 1i, and find that our first output for the function is 1 plus 3i. This first output falls outside our circle of radius 2, so we know that the original input number 1 plus 1i is definitely not within the set. To distinguish this number, let's color the point red, and if we perform one iteration of the function for every number within the circle, each number whose first output escapes the circle will also be colored red. Now let's iterate the function again for every number within the black region. Each number whose output escapes the circle after the second iteration will be colored green. Now let's do it a third time using the color blue, and a fourth time with yellow. Now let's take it up to 20 iterations, repeating these four colors to display all the numbers whose outputs escape the circle at each successive iteration. As you can see, every iteration excludes more numbers from the Mandelbrot set. By the 20th iteration, not much seems to be happening. From our distance, the last color bands are too small to see. However, if we zoom into a small region of the edge of the set, we can clearly see the results of 20 more iterations. And another 20. With each successive iteration, new details appear, making the edge of the Mandelbrot set increasingly convoluted. The edge can never be fully realized, because it would take an infinite number of iterations to draw the complete boundary. And since there is an infinite supply of numbers between any 2 points on the complex plane, we could keep zooming in forever, always revealing new details and never reaching the end. If we could perform an infinite number of iterations, we could see that the boundary of the Mandelbrot set is infinitely long, even though it's completely contained inside a circle with a radius of 2. And as weird as the outline of this entire set is, it isn't nearly as interesting as the details in the area around it, color-coded by how many iterations it takes to escape it. The choice of colors is completely arbitrary. Any sequence of colors can be used to display the same information. Unlike the Mandelbrot set itself, any series of colors used to display it is finite. So once a color sequence is over, we just repeat it for subsequent iterations. On this disk, the color palettes are customized to give each zoom its own unique flavor, highlighting specific details for maximum effect. But don't be fooled by the manipulation of color. The Mandelbrot set was discovered, not invented. These patterns are woven into the very fabric of nature, expressed in the eternal, universal language of mathematics. The big question is, what does it all mean? The most honest answer to that question is, no one knows. Modern computers have given us the ability to peer deep into the complex plane, opening up a whole new world of mathematical wonder. But computers can't give us the power to understand what we're seeing. Someday, we may discover a link between the Mandelbrot set and the processes that guide the laws of nature. Once you've seen the pictures, some connection seems obvious. But up until now, no one has even ventured a guess.